Hello everyone. Now, the third type of null hypothesis that is generally of interest to people is known as sphericity. Okay, so what is testing for sphericity? Let me write down the null hypothesis, then it would be clear. So I have now single population. So now I am not talking about multiple populations. I have a single population which is of dimension p. So x comes from p variate normal distribution with mean mu variance covariance matrix sigma. Then under h naught my sigma is sigma square into identity matrix, of course of the appropriate order. So what does this mean? This means that under h naught my sigma matrix is sigma square, sigma square, sigma square, and then 0 0 0 0 0 0 and so on. Have you come across this sort of matrix somewhere in other course or maybe in this course in the past?
Yes, ma'am.
Okay, where?
In the principal component analysis.
Correct. In PCA we have handled this type of matrix, and in any other course that is perhaps of more interest, because you know we are learning these things, so you should know why we are learning these things. So for independence I told you that in unpaired type of Hotelling test or in MANOVA you need independence of populations, and hence to examine the validity of assumptions we needed those tests. So the test that we did today and the test that we did in the earlier lecture. So where do we need this sort of test? Where do we need this sort of assumption? That the sigma matrix is a diagonal matrix with all the diagonal entries as same. Any guesses?
In your regression for your epsilon?
Correct. The residuals in regression model are supposed to be having constant variance. What is it called as in some fancy words? Constant variance assumption has some fancier name. What is it? Homoscedasticity. Correct. So you need homoscedasticity, which means that the variance should be constant for all residuals, that is the diagonal entries should be same, and you need the residuals to be uncorrelated with each other, so you need off diagonal entries to be 0. So this test would be needed for checking the for residual diagnostics in linear regression. Correct? Okay, so how should we proceed here? Now from whatever we have carried out so far, we know that in likelihood ratio test only the sigma contributes. The mu is here, the mu is anyway same. So my final test statistic would be in terms of determinant of sigma hat under h naught and determinant of sigma hat under no restrictions, that is under the overall parameter space. So what would be my sigma hat under overall parameter space? It would be my usual CSSP matrix by n. The crucial thing is what would be sigma hat under null hypothesis. So what would be sigma hat under null hypothesis in this case? I am supposed to have all the correlations to be 0. So of course I am not going to estimate that. So I should estimate only the diagonal entries, and that too I should have a common estimate for all the diagonal entries, because I want the diagonals entries to be constant. Correct? So I need a common estimate for all the diagonal entries. So from where would I get that? Yes? How would I get the common estimate of sigma square? Do you remember t-test from your BSc? How would you get the pooled variance? how did you get pooled variance in the t-test from BSc, two sample t-test? Hello? And now I want answer from someone else, not Pushkar. Am I audible?
Yes, ma'am.
Okay.
The period of 1 minus 1 into S1 plus N2 minus 1 into S2 square upon 1 plus N2 minus 1.
Correct. So in terms of CSSP things, if I want to write, so if my CSSP matrix this CSSP matrix is this S11, S22 up to SPP, then S12, of course S21 and S12 are going to be same, but P1, then here S1P, etc. Then I know that individual variance estimate for the first variable would be S11 upon n. For the second variable it would be S22 upon n, and so on. And hence the common thing would be 1 by P sum over I going from 1 to P Sii upon n. Are you following what is happening here? This is the exact generalization. This is an exact generalization of your t-test from BSc. So your S1 square was estimate, which was obtained by dividing by n minus 1. So you multiply by that n1 minus 1. But here this SII is anyway CSSP matrix. So it does the same job. So this is anyway sum of squares. Correct? Sum of squared deviations. So this SII, then you need to divide it by n because we want maximum likelihood estimates. We don't want unbiased estimates. And we need to pool over all P. So 1 by P sum over I going from 1 to P SII upon n. Okay so far? And then what would be the likelihood ratio? Sorry? Did someone say yes or did you ask doubt?
No, ma'am, I guess.
Okay. So the likelihood ratio test statistic, how would it be? It would again be in terms of supremum of likelihood under H naught divided by supremum of likelihood under overall parameter space. So I would have determinant of overall sigma and determinant of sigma naught hat whole thing raised to n by 2. Correct? Where sigma hat is this and sigma naught hat is this. Is it okay? And minus 2 log lambda would again follow chi square with say m degrees of freedom, where m would be difference between the number of parameters. So in the overall setup it is p into p plus p into p plus 1 by 2. Under null mu is not affected, so mu remains this. And for sigma, how many parameters are we estimating? How many parameters are we estimating from sigma? Yes?
P.
Are we estimating p different values? Yes. Oh, okay. There is a small mistake that I have made here and nobody pointed out. This is sigma square hat. This is scalar, right? And then you form sigma naught hat by putting this sigma square hat at the diagonal entries. Okay? You got what I'm saying? I wrote by mistake sigma naught here, hat here, but this is scalar. Every SII is a scalar. These are just diagonal entries of the CSSP matrix. So finally we are getting sigma square hat by this, and then that sigma square hat I would put in the diagonal entries here. That would give me sigma naught hat. So sigma naught hat is sigma square hat. Okay. So how many parameters are we estimating from sigma naught?
1.
1, because we are using the same value for all the diagonal entries, so we are actually estimating only one parameter. So I have only one here, so this would be p into p plus 1 by 2 minus 1. Therefore minus 2 log lambda would follow chi-square with these degrees of freedom. Okay, so this is known as test for sphericity. Okay, we'll stop here. We will continue on Friday. Thank you.